Hi everyone, welcome to part 17 of our series on the relational model. So this is the last video of this series. What we'll do is we'll do a quick recap of what we've done, how we've done it, and reach some conclusions. I'm going to talk a little bit about sort of the issues and so on that we found by doing this work, but I hope I will have some time to actually write the blog post, because I think the video might not be the best medium to discuss that. So without further ado, let's have a quick look at what was done. So this is the relational model that was created as part of this series of videos. So the idea, just going back to the beginning, the idea was that up to now we've had a log file, and I can show you a log file if I just hop over to one of these shells. I think on okay, so this is a classic Dogen log file you see here. Now, the log file for Dogen has been extremely useful. We create a lot of log data, and as you can see here, we tend to dump things in a JSON format in a log file. So this has enabled us to do very quick greps and sort of searches for data. And once we locate the data that we're interested in, we can very simply just do a JQ on that data, and then sort of browse the JSON, grab the JSON, and of course, you know, being Emacs, you have the full power of JSON. I mean, and on top of that, of course, you have the JQ mode, which I never quite remember how to use, JQ interactively, which enables you to do things such as a query, and you know, do all sorts of things with the data that you've got. So as you can see here, it's very useful. For example, if I just want to obtain type, you see very quickly I can obtain the type of all those artifacts you see there. So it says this has been extremely powerful, and we've used this a lot in Dogen development. But one of the problems we are finding now is that Dogen is becoming increasingly more complex. If I take, for example, a look at the assets model, so from sort of the beginning where we used to have a few meta types and assets model was quite trivial, you can see here now the assets model has grown a fair bit, and so I have the number of transforms in a chain, and of course assets is just one of the models that we've got. If I hop over to injection, we then have another pipeline. So Dogen is now very complex, and not is it just complex, but it's actually more of a graph rather than a linear thing. So when I'm looking at the data coming out of Dogen, a lot of the times I don't really want to see a flat linear sort of dump of the data. I want to see something a bit more graph-like. And we've been kind of doing that slowly by creating graphs, for example, for the references in the model. We've been creating the transform graph that enables you to see all the different transforms that we run for a given run, and you could sorry, our mode keys are still not quite fixed, and you could of course take the data from the graph and then go back to the log file, and then search for the GUIDs. Presumably this is not the latest run, but search for the GUID here, or the transform name. I mean, the GUIDs have moved since the last run, so I haven't generated tracing for the previous run. So if I just go over to the log file, to search for this transform, as you can see, and then very easily you could grep just for that one transform. This will give you the log of the transform. And if I could just do that shell command output, and as you can see, very quickly you could figure out from the graph what's happening in terms of the log and so on. These are just basically ways that we've been trying to cope with the fact that the log is a linear representation of what it is really a deeply nested graph in reality. And that deeply nested graph is much easier to see in graph form than it is to see in flat form. So the problem we had is that sometimes you need to run very complex queries. So sometimes you don't really know So say for example I look at the dumped models from the top level transforms. Say for instance that we need to figure out whether a type existed up to a point in our chain and then suddenly disappeared somewhere in between, say, injection and extraction. So for these cases it's actually quite difficult to run this kind of queries, because you'll have to look at each of these sort of dumps of the transforms, and then you have to do a dump of the JSON, and then you have to run a grep. And of course you could script these things and so forth, but it just seemed intuitively like we were doing something that was not natural for the data format that we had. So it occurred to us that perhaps the best thing to do is simply to just take all of the data that we generate in Dogen, including the logging, and dump it over to a relational database. And that's how this series of videos started. It at the time seemed like a simple thing to do, as it always is with programming. It wasn't quite as simple as we thought, and the model went through a series of iterations. It started by being a really sort of strongly typed, I guess we could say, relational model with lots of tables. But then we soon concluded that in order to populate that relational model, we would have to have a lot of code inside of Dogen that does the decomposition and normalization of the graphs, such as complex graphs we have in each of these representations, over to the SQL representation, to the relational representation. And that seemed like a lot of work. So instead we thought, well, why don't we just dump the JSON data that we have, and that's literally what we have in the file system at present, over to SQL. And then, of course, Postgres has got such great JSON support and XML support. We could just use Postgres' features to try to extract the data from the JSON, just like we do with JSON JQ. But of course, JQ is more of a one-off thing, whereas in Postgres we could write proper functions and have queries in a library of queries that do exactly what we want, and we could evolve those queries over time. So that was the vision eventually, and then this series of 17 videos was sort of the process of getting to that vision, to realizing that vision. And so at present we now have all the code is generated, all the problems we had with ODB have been fixed, all the problems we had with Dogen have been fixed. We can now generate the ORM code exactly as we wanted it, and we extended our tracing in a fairly clean manner, not exactly perfect, but not too bad. We extended tracing such that the tracer now has backends. Backends are talking in terms of strings. We implemented default backend, which is a file backend, which does what it did in the past. But we also implemented relational backend, which is this chap you see here. And the relational backend writes all the tracing data into the database. We also created a log backend, but here the word backend is a bit of a misnomer. Well, it's not a misnomer, it just has a different meaning. It means a boost log backend rather than a tracing backend. And this boost log backend writes all of the log file data over to the database. And it's fairly clean, not perfect, but it's fairly clean. We didn't lose too much in terms of performance. The happy path continues to be what we wanted, which is fairly quick. The not so happy path with full debugging and logging is a bit slow. For the entirety of Dogen it takes about 45 minutes, 50 minutes maybe, to generate all models. So it kind of, if you have a serious problem, then you should use this feature. If you don't, then just disable it and generate in a few seconds, as we always did. So what do we do in terms of the database then? If I hop over to our SQL view here, so we created a series of functions, as you can see here. So if I just dump the functions, created a series of functions that enable us to obtain data from a run. Once the run is finished, then everything is uploaded. So for example, you could say, tell me what runs you got in Postgres. You see, you've got quite a few here. And it tells you when the run was. It's also possible to obtain a target for a run. So if I just say select start from, hopefully this will show us what model we were running. The way this works is if I just say select star from log event limit 10. Sorry, one thing that we did do is use this approach of naming the tables with quotes, which is not ideal. So as you can see here, I can just do a select star from the log database, log table, and I see the log file here, as we saw a second ago. And of course I still have the exact same powers as we had before. I can still say, well, there's some JSON here, can you please JQ this JSON? And as we did before, this is very, very simple, very easy to do. As we did before, where you're interested in saying, well, I just care about a certain component, it's also very simple to just do a filtering function that says, please give me all the logging I got for any transform. So this is in itself already very powerful. I can just go and look at the log file. I can relate the log file with the transforms, and I can do all sorts of querying and filtering. So the functions that we created enable us to obtain some canned behavior, I guess. So for example, say I'd like to see a configuration for a run, for instance. I could just basically say select start from configuration for a run. I choose a run ID, this chap here, and away it goes, and it gives me the configuration. This particular case is already doing JSON pretty, so it's very easy to obtain the configuration for the run. So I guess these are the good news. We are able to do a lot of very interesting querying in the database. What I'll do is just want to show you one more thing, query that I already ran. So if we quickly have a look here at the transforms, so these are a series of transforms that are using dia, and I could quickly just grab the transform instance ID, this chap here. And then I could say, well, can you please tell me what dia objects do I have in this diagram? And that's quite simple. Of course I need to quote this. So if we just do select star from this function, as you can see here is quite a few objects. The reason why you're having the duplicate is because it's showing every single attribute of every single object. If you just want the dia objects themselves, of course you can use this chap here, and this will just give us names. Actually just gives us the raw object, so you can then do whatever you like with it. As you can see, once we start dumping heavy amounts of JSON, especially very long line JSON, sadly we tend to see Emacs kind of slowing down a little bit, which is a bit annoying. So this is one disadvantage of using the JSON a bit too much in anger. So what we tend to do instead is we tend to selectively look for JSON. So it's sort of, instead of dumping big JSON objects, the idea is to try to locate the more significant bits of JSON, and then have those as the output of the function, so that we don't slow down Emacs too much. It would be nice, so as you can see, once Emacs starts behaving like this, the life becomes a bit hard. So what you can do, if you do a dump of a lot of JSON in Emacs, is just get rid of it, because otherwise Emacs becomes somewhat unbearable. So what we'll do is we'll just capture this JSON, and it's nothing to do with JSON, it's to do with long lines, to be fair. One day hopefully we'll have a Postgres, an Emacs that copes with very long lines, but that's not the case. So as you can see here, all these functions give you very, very clever ways of obtaining bits of data. And what we did is we using this, we iterate it through the transforms. I can't actually show you that right now because at the moment the transforms are... Well, actually, what I'll do is I'm going to modify this function to return sort of a cut down version of the JSON, just purely so you can see. Actually, once you start faffing around with the function types, Postgres is no longer happy to replace a function, so you have to drop it manually, which is a bit of a shame. Okay, so now that we have this function, then what we'll do is I'm just gonna dump transforms for a given run. So if we oh, actually we need to remember what our run ID was, which I entirely forgot. So if we choose one of these run IDs, such as for example Dogen.dia, which is a very small diagram, and we just call this chap. As you can see, what we do here is we basically ask the database to give us every single entry, every single transform in our transform graph, and for each of these, of course, you can see the JSON and the payload, and also, quite interestingly, we can see the payload type. So once you know the type of the model, you can start to run queries that are specific to a given type of a model. So for instance, if I would like to query all of my files looking for a specific file name, or even if I'd like to see every single file in the model, say for example, okay, this query seems to have gone, presumably because we've probably changed the... Yes, the problem is that with the hashes no longer match, so what we'll do, this is a slight problem, downside of having GUIDs. Every time you do a run, the GUIDs change, so our queries don't execute cleanly anymore. But say for example we go here, we locate a dia model, such as this chap here, and we get his transform instance ID. And now we could update our transform instance ID to this chap, and hopefully okay, now you see the problem of the change I did a second ago. Of course, these functions need to return JSON-B because we use a lot of composition, and what we do is we have functions that return the massive JSON-B payloads, and then we have other functions that take those JSON-B payloads and query them, such as this chap here. And if you start changing things to text, then the functions don't work anymore. Right, so now then, we don't seem to be able to find okay, right, then my mistake. Of course, as you can see here, this method is requesting a run, and I supplied it with a transform ID. So if I was to look for the run itself, to be fair, probably was what we had there a second ago, but so this chap here, hopefully, as you can see, what this did is it basically looked for every single file that was generated for that given run. And you can see these files, and you can see the transform that generated them. And you could see the content, you could see pretty much everything there of the file. If you wanted to, you could grab for the content and look for things inside of the file. So this is, I guess, the good news. The good news is you can imagine you can extend this library of functions, and you can start to create more and more complex queries. And we did, as part of this exercise, we did queries that find lots of different things, such as all the types in a generation model, We look specifically for registrars in the assets model. We looked for all sorts of things as part of this exercise. You can see there's many queries were written. And in one side we could say, or on one hand we could say, this is extremely powerful. This is really what we envisaged has come to pass. On the other hand, this is actually not as useful as we thought it would be. Reason being that writing these queries is actually quite difficult. It requires a lot of knowledge, in-depth knowledge of the data structures, and in-depth knowledge of JSON-based syntax in Postgres. So as you can see here, these queries are non-trivial, and once you start doing things such as joins, it's easy to make mistakes, and then you end up not finding the right data, not because there's a bug, but because there's a bug in your query, not because there's a bug in Dogen, I mean. And it could lead to false positives. So the query writing is in itself a mini project, really, not quite as quick and simple as we'd have thought it would be, as if we had, say, a relational model that was completely decomposed into, normalized, say, into proper tables. That would make it easier to write these queries, but of course harder to write the decomposition code to normalize Dogen graphs. This is a non-trivial task. So by the end of it, though we used this quite successfully to detect the problem with registrar, which was, by the way, a very simple problem. We had forgotten to update one of our sort of iterating functions to take into account the new meta type. Our general conclusion has been that it is probably easier to create a process for adding new meta types that takes into account all the steps that are required, and you just have a checklist. And when you add a new meta type, you go to that checklist and make sure that you've done all the steps. And then it is to write queries that take into account all sorts of vagaries and permutations of all possibilities that could happen in the transform. So I think we will use the relational model, but I don't think we're going to use it as much as we thought we would. I think it's just a little bit too cumbersome to use right now. So I guess after such a hard sort of slog, such a difficult task of almost an entire sprint plus some of the other previous sprints as well, it's a bit disappointing, a bit of a low, I guess, that is not quite as useful as we thought it would be. But the other way to look at it is that not only is this a PhD project in the sense that you have to do lots of exploration, but it made us conclude that maybe programming is itself a PhD project. Experimentation is just part of the life of a programmer. Sometimes you think something is going to work really well, but until you've done it, until you've actually started using it in anger, you can't really tell, unless you've done it before, of course. And so that's kind of the general conclusion we've made here with the relational model. It is useful, but not as useful as we thought it would be. So I guess it's slightly less upbeat than we would have been when we started this task. But nevertheless, it was a very interesting journey. It led us to improve Dogen quite a lot, and it also led us to see what happens when you use Dogen in anger with the ORM model, which was very positive. It led us to a lot of fixes in the ORM model, and it may lead us to more useful functionality. It's just not as useful as we thought it would be for the case of meta types. And so on that note, we conclude then our 17th video of the relational model. Thanks very much for watching.